So hello guys, this is the second part of our discussion of improper integrals. In the first part, we discussed the first type of the improper integrals. We have the unbounded or infinite domain. So on the second type, we will do um, discontinuous integrands. So for this type, we will consider discontinuous function. Okay? So like I said on the first type, before we discuss that, um, these were the conditions for or the assumptions for the fundamental theorem of calculus. On the first type, we look at this assumption here. Suppose it is not true. Now, on the second type, we will do this second assumption in here. We suppose that this is not true. Okay? We suppose that that is not true. So we assume that we have discontinuous function. For example, here, suppose the function here is discontinuous at b. So this will just go up and up and up there. Okay? What we can do is maybe we start chopping or we start looking at the area, okay, of the region bounded by the graph over the interval a up to k. In here, k is less than b. Okay? And looking at this illustration, it seems that we have a definite integral and it has an area. We have this region and we can calculate the area. Okay? So what we're going to do here is to let our k approach b. So for example, if our k is now in here, then we will have this part here. We include that region. And if our k is now in here, we now increase further. So we will include this region here, and so on and so forth. So we will let our k to approach b on this side of b. Okay? So this is now the type 2 for the improper integrals. We consider discontinuous integrands, discontinuous functions. Okay? So in here, we assume that the function f is continuous on this half-open interval. So from a up to b, including a but not b. So continuous on this half-open interval. And we assume that f is discontinuous at b. Okay? So we define this improper integral. Improper integral of f of x dx from a to b. Okay? It seems definite integral. It looks like a definite integral, but it is not. Okay? Because in here, the function is discontinuous at this limit of integration here, according to this assumption. Discontinuous at b. So this is an improper integral. And in order to calculate this, we go to this limit here. So notice, we rewrite this or we define this improper integral as the definite integral, or we take the limit as t approaches b from the left of the definite integral of f of x dx from A to T. Okay? So if we look at this, say this is your real line. Okay? This is your A in here, this is your B in here. So we assume that the function is discontinuous in here. We have our T, so we consider this. We have our T here, we consider this in this interval now. Or we put our T here, then we consider this. So we let our T approach to B. And it is on the left side of B, that's why you have this. Limit as T approaches B from the left. Okay? Of the definite integral of f of x dx from A up to T. And then similarly, suppose we have the function f continuous on the half open interval A up to B, this time discontinuous at A. Okay? So we define this improper integral f of x dx from A to B, okay, as the limit as t approaches A from the right of the definite integral of f of x dx from T to B. So this time, you have this is your A here, and this is your B. So your T may be somewhere here, and we let this go to A. So it's on the right side of A, so we approach T, we let T go to A from the right. Okay? And just like before, if the corresponding limits here exist, then we say that the improper integral is convergent. And otherwise, we say it is divergent. Okay? Now, suppose the discontinuity is in the middle. So if f has a discontinuity at C, where C is between A and B, and both, take note of that, and both improper integrals here. Because f has a discontinuity at C, we have the interval A to C. That's an improper integral then. That will define an improper integral then. And then in here, we have the interval C to B. And again, f has a discontinuity at C. This guy here will define another improper integral. But if both of them are convergent, okay, then we define this improper integral f of x dx from A to B. Okay, we write it like this. So the improper integral of f of x dx from A to C plus the improper integral of f of x dx from C to B. Okay? Questions? So again, we need these two guys here to be to exist. Okay? So we need these two guys here to be both convergent so that this is convergent. If at least one of them is divergent, this will be divergent. Okay? If at least one of them is divergent, then this is divergent. Okay? So this is that third case. We have the interval AB, but the function is actually discontinuous at C. Okay? So we consider the interval A to C, and then we consider the interval C to B. We check the convergence of both improper integrals here. If they are both convergent, then as a whole, it will be convergent. If at least one is divergent, then as a whole, the improper integral is also divergent. Okay? Let us consider this example. So we want to find the integral from -3 to 2 of 1 over square root of x plus 3 dx. Now, looking at this, of course, the domain of your function here, okay, if you look at this, your x plus 3 must be greater than 0. And take note, I don't have the equality in here because square root of x plus 3, it's on the denominator. So we cannot have the denominator to be 0. Okay? So we have here x greater than -3. So this function here, 1 over square root of x plus 3, it's defined for all x greater than -3. But the lower limit of integration here, it's -3. So this guy here, it's an improper integral. So we do it, -3 to 2, 1 over, or dx over square root of x plus 3. And again, we do this by definition, meaning since this is an improper integral, you need to write the limit thing. So this guy here, it's equal to the limit as t approaches -3 from the right. Okay, so -3 from the right of the integral from t up to 2 of dx over square root of x plus 3. Okay, so let me do this completely. You have the following. The integral from t up to 2 of dx over square root of x plus 3. Maybe you want to do some u substitution. Let u be equal to x plus 3. Du will be dx. Okay? So this guy here, it's just the integral from du over square root of u. And this will be what? 2 square root of u, okay, plus c. Take note of this, 2 square root of u plus c. Or we bring back x. We have 2 square root of x plus 3 evaluated from 2 to 2, t to 2. So this is just 2 square root of 2 plus 3 minus 2 square root of t plus 3. Okay? And then let's bring this to the numerator here. I mean to the integral here. We'll just have the limit as t approaches -3 from the right of 2 square root of 5 minus 2 square root of t plus 3. And as t goes to -3 from the right, look at this. Your t approaches -3 from the right, which means your t is greater than -3. So this is still satisfied. And therefore, this is still well defined. 3 plus something greater than -3, that is positive number. But if your t is very, very, very close to -3, this will be very, very, very close to 0. So the answer here will be 2 square root of 5. So this guy here, it's convergent. And the answer is 2 square root of 5. Okay. Questions? Next problem here. Determine whether this integral here from 0 to pi over 2 of tangent x dx converges or diverges. Now recall tangent function, okay? The graph of the tangent function. So this is your pi over 2, okay? And we just need from 0 to pi over 2. So I'll just do this part here. This will be something like this, okay? So this is the portion of y equals tangent of x. Okay? So it means tangent of x, it's discontinuous at pi over 2. So this is an improper integral. So we write integral from 0 to pi over 2 of tangent x dx. This is the limit as t approaches pi over 2 from the left. Okay, pi over 2 from the left of the integral from 0 to t tangent of x dx. Okay, but what's the integral of tangent of x dx? It's ln of secant x. Okay, so we have the limit as t approaches pi over 2 from the left of ln, absolute value of secant x, evaluated from 0 to t. Or this is just the limit as t approaches pi over 2 from the left of ln of secant of t minus ln of secant of 0. Secant of 0, it's 1. Ln of 1, it's 0. Okay? So this guy here, it will go to 0. This guy here. Well, it is equal to 0. Secant of 0, that's 1. So ln of 1, that's 0. For ln of secant t, as t approaches pi over 2 from the left. So again, graph. This is your pi over 2. The graph of your secant t is something like this. So this is at 0. This is your 1. So you have something like this. And on this side, you have something like this also. But yeah, as you can see, secant 0, at least believe me that this is the graph, at least at this part. And at this point, at x equals 0, that's 1. So secant of 0, that's 1. Ln of 1, that's 0. But as t approaches pi over 2 from the left, this guy here will be going to plus infinity. Okay? And therefore, you have ln of the absolute value of something going to plus infinity. Okay? It will also go to plus infinity. So let me just write here, this is y equals secant of x, and ln of something going to plus infinity, this is also plus infinity. So this guy here is divergent. Okay? So integral from 0 to pi over 2 of tangent x dx is divergent. Any questions? Next, evaluate the integral from 0 to 3 of dx over x minus 2. So x minus 2 here, it's on the denominator. So you don't want this to be 0. So you don't want your x to be 2. But 2, it's just inside this interval. So this guy here, this is improper. This guy here, I mean the whole thing here, it's an improper integral. Because it is an improper integral, we divide this into two parts, particularly at the point of discontinuity. So integral from 0 to 3 of dx over x minus 2, this is equal to the integral from 0 to 2 dx over x minus 2 plus integral from 2 to 3, this is dx over x minus 2. Okay? So from here, we use the definition. We write now the definition. We now have the limit. As t approaches to from the left, integral from 0 to t of dx over x minus 2 plus limit as s approaches 2 from the right. So take note, I use t in here. I should use another parameter in here or another variable. So I am using s. And the integral is from s up to 3 of dx over x minus 2. And then let's check both of them, or maybe just one of them, if if we got lucky and we were able to solve that at least one is divergent already. So we will stop. Okay. For instance, let us check this guy here. So we have the integral from 0 to t of dx over x minus 2. Okay. This is just what? Ln absolute value of x minus 2 evaluated from 0 to t. And this is equal to the ln of absolute value of t minus 2 minus ln of absolute value of negative 2. Okay? So for this part, we get the limit. Okay? And then let's see. Let's see what will happen there. We have now the limit as t approaches to from the left of ln, absolute value of t minus 2 minus ln of 2. Okay? Absolute value of negative 2, that's just positive 2. But this guy here, as t approaches to from the left, this will just be 2 minus 2. And that's 0. And ln of 0, that's negative infinity. Okay? So in here, we will get some negative infinity plus whatever in here. But the point here is this is already divergent. Okay? So let me just write it here, and I'm just gonna copy this part. Okay. Just gonna copy this and here. But this is already negative infinity, meaning this is divergent. The whole thing must be divergent. Okay?
So wouldn't the
Yes.
wouldn't the limit just not exist? Because like if you're taking the lawn of point, like it's a negative number, right? Because you're approaching from the left.
But you have absolute value in the
Oh,
way.
right. Okay.
So it's just positive again.
Okay. Thank you.
You're welcome. So the integral or the improper integral from 0 to 3 of dx over x minus 2 is divergent since this integral, okay, dx over x minus 2 is divergent. In fact, both of them, if you calculate this, you'll get divergent also. Okay? But it's enough to solve for one of them. Questions? Now, a lot of students are careless. They do this definite integral, okay, without realizing the discontinuity at the middle. If you do this without realizing the discontinuity at the middle, you'll get some answer in here. And definitely that's wrong. You won't get any point on that. Maybe I can give you 5 points for knowing that this is ln something. Okay? So take note of those discontinuities. Okay? Next, find the improper integral 0 to 1 of ln of x dx. So for this, remember we already did integral of ln of x dx. So we can use that. But again, ln of x, this is discontinuous at 0, at least using this interval here. Your x must be greater than 0 in here. So the discontinuity is at 0 in here. Therefore, we have the integral from 0 to 1, ln of x dx. This is equal to the limit as t approaches 0 from the right of the integral from t to 1 of ln of x dx. Okay? And in here, I'll skip some details for this. Try to check again that the integral of ln of x dx, it's x ln of x minus x. So I'll just write that directly in here. We have the limit as t approaches 0 of x ln of x minus x evaluated from t up to 1. And this will be the limit as t approaches 0 from the right of t ln of t minus, sorry, it's 1 ln of 1. So we are evaluating. So it will be 1 ln of 1 minus 1 and then minus t ln of t minus t. Okay? Of course, ln of 1, that's just 0. And then we have minus 1 in here. And then we try to find the limit of this as t approaches 0 from the right. So if we do that, we'll just get minus 1. And of course, in here, as t approaches 0, this will just go to 0. And we will have minus the limit as t approaches 0 from the right of t ln of t. But this limit here, okay, this limit here, this is again infinity times 0. It's an indeterminate form, infinity times 0. As t goes to 0, this will go to 0. On the other hand, in here, this will go to negative infinity. So 0 times negative infinity. So the limit is an indeterminate form of infinity times 0. And then just like what we did in a previous example, we rewrite this so that we can apply L'Hopital's rule. In particular, we rewrite this as ln of t divided by 1 over t. So this guy here, you can rewrite it as this guy here. And as t goes to 0 from the right, this will be infinity over infinity. And which means we can apply L'Hopital's rule. Okay? So we apply here L'Hopital's. Still have negative 1 in here. Then minus. We have the limit as t approaches 0 from the right. And then derivative of ln of t, that's 1 over t, over derivative of 1 over t, that's negative 1 over t squared. Okay? And then let's just simplify this. You have negative 1 minus limit as t approaches 0 from the right, 1 over t over negative 1 over t squared, that's just negative t. So as t approaches 0 from the right, this is just 0. So the answer will just be negative 1. So this integral here is convergent, and the answer is negative 1. Okay? So that's the second type of improper integrals. Okay? So let me recall the first type. The first type here, it's the unbounded or infinite domain. So the intervals will be, so for this case, you have the interval 1 to plus infinity. For this, you have the interval negative infinity to b. And for this, you have the, so for number 3 here, you have the interval negative infinity to plus infinity. Oops, sorry, that should be open. So from negative infinity to plus infinity. So unbounded interval or unbounded domain. For the second type, we have discontinuous integrand. So in here, we have this interval, but the function is discontinuous on the left, on the right endpoint. In here, we have discontinuity on the left endpoint. In here, the discontinuity is between the interval, or between or in the middle of the endpoints. So you have the interval a comma b. Okay, you have the interval a comma b, but your c, it's somewhere inside. Okay, somewhere inside, and the discontinuity occurs at that c. So that's type 2 improper integrals. Okay. Now, to finish the topic, we have what we call a comparison test for improper integrals. Okay. So what is this? Suppose f and g are continuous. Okay. With this property, 0 less than or equal to g of x less than or equal to f of x for all x greater than or equal to a. Okay. So for example, this is your a here. Maybe your function f of x is something like this. So f of x in here. And then your function g of x, it's something like this. So g of x in here. So we are assuming that f of x is greater than or equal to g of x. Okay. Of course, before a, okay, on the left of a, we see here that the graph of g is greater than or it's above the graph of f. We don't care about that. We want our x to be greater than or equal to a, and this is satisfied. Okay. Now, if the improper integral of f of x dx from a to plus infinity is convergent, then the improper integral of g of x dx from a to plus infinity will also be convergent. Okay? Intuitively, I say this statement like this. If something is bigger is convergent, okay, then the one smaller must also be convergent. But of course, you have this restriction here. You have this 0 here. Okay? The other statement is this. If the improper integral of g of x dx from a to plus infinity is divergent, then the improper integral of f of x dx from a to plus infinity will also be divergent. Okay? So intuitively, I say it like this. If something smaller is already divergent, then the bigger one will also be divergent. Okay? So for example, show that integral from 0 to negative infinity, from 0 to plus infinity of e to the minus x cubed dx is convergent. So we want to show that this is convergent. So how do we do this? Look at this. On the interval 0 to plus infinity, okay? On the interval from 0 to plus infinity, the value of x will be less than x cubed. In fact, no, not from 0. From 1. Okay? So from 1 to plus infinity, the value of x will be less than x cubed. Okay? And then, therefore, this means that negative x, this will be greater than negative x cubed. Okay? There was a comment. Isn't it excluding 1? You are correct. So let me put the equality. And now we still have the valid inequality here. Thank you for that. So on the interval 1 to plus infinity, we have x less than or equal to x cubed. And therefore, if we put negative, the inequality will be reversed. Okay? This means that e to the minus x, this is greater than or equal to e to the minus x cubed. But exponential function, this is greater than 0. So we have this. So if we can show that the integral of e to the minus x is convergent, then this guy here, the integral of this, will also be convergent from the interval 0 to plus infinity. Okay? But we will only need the interval 1 to plus infinity. Okay? The integral from 0 to 1 of e to the minus x cubed dx, this is always finite. This is finite. Because e to the minus x cubed, it is continuous from 0 to 1, but this is definite integral. This is not improper integral here. So you can calculate the value of this. Okay? The problem is from 1 to plus infinity. But this is what we know. We have 0 less than or equal to the integral from 1 up to plus infinity of e to the minus x cubed dx. This will be less than or equal to the integral from 1 to plus infinity of e to the minus x dx. So if we can show that this is convergent, definitely this will also be convergent. That's the comparison test. But this guy, we can easily calculate this. The integral from 1 to plus infinity of e to the minus x dx, this is equal to the limit as t approaches plus infinity of the integral from 1 up to t e to the minus x dx. Well, this is just the limit as t approaches plus infinity of negative e to the minus x evaluated from 1 up to t. This is equal to the limit as t approaches plus infinity of negative e to the minus t minus negative e to the minus 1. Okay? But as t goes to plus infinity, we will have here e to the minus t. And minus t will go to minus infinity. This guy here will just go to 0. So we will have here e to the minus 1. This means that the improper integral from 1 up to plus infinity of e to the minus x dx is convergent. Okay? So the integral from 1 up to plus infinity of e to the minus x cubed dx is also convergent. And of course, this is just finite. So all in all, this is convergent. So since integral from 0 to 1 of e to the minus x cubed dx is convergent, or it's finite, the integral from 0 to plus infinity of e to the minus x cubed dx is convergent. And that's the proof for this improper integral here. Okay? Lastly, we have this. Show that this integral here, integral from 0 to plus infinity, of 1 plus e to the minus x cubed over x dx is divergent. Okay? So, how do we do this? Well, on the interval 0 to plus infinity, in fact, we have the open interval here. On this interval, 1 over x will be positive, but this will be less than 1 plus e to the minus x cubed over x. Correct? Because you added something in the numerator, and what you added is positive. So definitely, this guy here will be greater than this. Okay? And for this, we only need to consider this guy here. We show that on the interval 0 to plus infinity, this is divergent. What we're going to look at is the integral from 0 to 1 of dx over x. This is improper because the lower limit of integration here, it's 0. So this is just the limit as t approaches 0 from the right of the integral from t to 1 of dx over x. But if we calculate this, we just have the limit as t goes to 0 from the right of ln, absolute value of x, evaluated from t up to 1. So this is the limit as t approaches 0 from the right of ln of 1. Again, that's just 0 minus ln of t. I am removing the absolute values because, well, 1 is positive. We let our t to approach 0 from the right. So t is also positive. So I can remove the absolute values. But what does this mean? As t approaches 0 from the right, ln of t will go to negative infinity. So this will just be negative of negative infinity, and this is plus infinity. But what's the point? This improper integral here, it's already divergent. So integral from 0 up to 1 of dx over x is divergent. And so integral from 0 to plus infinity of dx over x, this is also divergent. is also divergent. And therefore, the one bigger, this guy here, it's also divergent by the comparison test for improper integrals. So therefore, the integral from 0 to plus infinity of 1 plus e to the minus x cubed over x dx is also divergent.